All right, I think we're live and ready to go. Sorry about the delay. Last time we were talking about kinetic isotope effects. We talked about the way these things happen, and it involves, if we imagine a bond between some kind of bond between some atom and hydrogen, and if we were to draw just the Morse potential for that bond, we would have seen that the ground state vibrational energy level for the, say, bond with the atom and deuterium is lower than the ground state for the bond with hydrogen. And remember that vibrational energy levels are 1/2. I forget what they are. Should have looked that formula up. 1/2 plus n or something like that. Yeah. Sorry. So it's 1/2 plus n, where n is an integer, times Planck's constant times the frequency of vibration. So when n equals 0, it's just 1/2 Planck's constant times the vibrational frequency. And then remember that we said the vibrational frequency was a function of a couple of things. First, you've got a force constant, which I'm going to call F. Your book calls it K, but there's too dang many K's in this chapter, so we're going to just use F. And then a reduced mass, which is equal to mass 1 times mass 2 divided by mass 1 plus mass 2. And it's this reduced mass that changes a lot when you go from hydrogen to deuterium. And you can run the numbers out and figure and demonstrate to yourself that there's a difference in the energy levels for n equals 0 for proton versus n equals 0 for deuterium. Now, the difference in energy between these two levels we talked about, we're going to call that 0-point energy difference. Okay, so that's the basic fundamental principle. Now, how does this influence reaction rates? We did sort of a crude thought experiment. Crude meaning rough and not accurate, not like vulgar or inappropriate. We thought, what would be the energy difference to completely break the XH bond versus the XD bond? And so I'm going to draw a dotted line sort of up here where the Morse potential goes to sort of 0 at infinity, and we're going to call this bond homolysis. In other words, this is complete bond breakage. Understand that we're going to use this as a way to define kinetic isotope effects, but understand in reality, in transition states, bonds are rarely completely broken. And so what we've mentioned last time and now is sort of going to be the limiting case, and our actual observations are going to be somewhat less than this. So remember last time we said the energy to get up to bond homolysis for deuterium is greater than the energy to get from proton to bond homolysis. And just because of maths, you can say that this difference in 0-point energies is also equal to the difference between energy to break the bond with deuterium minus the energy to break the bond with hydrogen. Okay? And if our reaction, if the transition state really involved complete bond homolysis, what we would see is that the rate for the reaction with proton would be much faster, would be significantly faster than the rate for the reaction with deuterium. And we showed that that was the case last time using some equations for rate constant as a function of activation energy. And basically we said that the rate constant for bond homolysis for a proton involved bond versus deuterium involved bond can have a maximum value sort of around 7. But if the XH or bond isn't totally broken, it might be less. And it actually gets more complicated than that. And I've had to learn a lot of PChem that I didn't know about vibrational modes, which sort of had to read through it twice, and it was really kind of annoying. But I thought I'd present the problem to you so you could understand sort of what we're thinking about. So imagine a reaction coordinate diagram, and we'll have a transition state here, and there's the product. So this is a reaction that's basically isoenergetic. You have starting materials, you have products, and then you have a transition state. Okay? And let's imagine that this is just a proton transfer reaction. So you have your acid, you have some base, and then after, and I guess probably we'll draw things like this. Nope. Try again. And then after the reaction, you have your conjugate base of your acid, and then your protonated base. All right? And let's suppose that the transition state is sort of looks like this, where the bonds are equally formed and broken respectively. All right? Now, and on the x-axis is going to be our reaction coordinate, which we could describe in a couple of ways. The reaction coordinate involves movement of the proton from being with A to being with B. And it actually turns out that you can model this reaction coordinate on an interesting vibrational mode that develops as the reaction proceeds. So that vibrational mode looks like this. Here's A, H, and B. And here is sort of the regular bond vibration of the bond between A and H. But then if we allow the B to sort of vibrate in the other direction, you can see that as we if we were to follow this vibration completely, we'd break the bond between A and H, and we'd make a new bond between H and B. So this vibrational mode is our reaction coordinate. Moving moving the proton from here to here is going to get our reaction to happen, and so that's the change in geometry that's played out for us on this reaction coordinate diagram. And I should say that the y-axis is energy. All right, but there are other vibrational modes that don't lead to product, and I'm trying to remember if we talked about these last time. I've got to go check and see what we did. Sort of, but not. do you remember last time we talked about a reaction coordinate where at each point along the reaction coordinate, what you actually have is a perpendicular valley that describes the non-productive vibrational modes, the other things that can go on in the molecule. What's that? Cows, that's right. That's right. So this is a mountain pass. Your pathway is the reaction coordinate, and the sloping up of the mountains on either side of you is your vibrational energy well. And the cows bonking into each other and the sides of the mountain represent vibrations of some sort. Okay. So what this means is at each point along our reaction coordinate, we can take a slice in the perpendicular direction, and we should be able to see an energy well that corresponds to the vibrational modes available to the reaction geometry at that point. So what I'm going to do is shrink that down so we got a little bit more space. So let's just imagine, if we blow this up, let's just imagine that in the perpendicular direction, we've got a vibrational energy well that looks like this. Okay? And this is going to correspond to vibrations in the starting material. And in the starting material, the base is clear way far away, and all we've got is our acid. And so this starting material vibrational node is just going to represent, let's see, there we go, going to represent vibration of the HA bond. Okay, and this axis will be energy, and this axis is going to be vibration perpendicular to the reaction coordinate. And I'll just draw the gray panel to remind you that we've taken a slice of the three-dimensional reaction coordinate at the starting material, and this is the cross-section that we're seeing. You okay with that? Sort of blowing my brain up a little bit. So this would be where, say, the A deuterium bond would be, and let's say this would be, I'm exaggerating, this would be where the 0 point energy for the A hydrogen bond would be. All right. And as I think I've demonstrated through what we talked about last time, but I can maybe show it to you. Are you ready for some maths? I'm sorry, this gets really P-chemy. I really am, but it was helpful to me to understand this. So you've got this energy of vibration for H, and you have this other energy of vibration for deuterium. And the difference in energy, we're going to call that the 0 point energy, right? 0 point energy difference should equal 1/2 times Planck's constant times frequency of hydrogen vibrating minus 1/2 Planck's constant times frequency of deuterium vibrating. Okay, with me so far? And we've said that that frequency equals 1/2 pi times the square root of force constant. And we're going to say this is the force constant of our starting material because we've taken the slice of our starting material. And then we're going to divide that by the reduced mass for the proton. Okay? For the proton HA bond or something like that. All right? So that would be the frequency for the proton. The frequency for the deuterium is going to involve the same force constant, but it's going to be divided by the reduced mass for the deuterium acid bond. And if you want to substitute these expressions, oops, want to substitute what I've written here in for the vibration of the proton, and then what I've written here in for the vibration of the deuteron, you will get the following equation for your difference, ZPE, difference in 0-point energy. And I'm doing this because I'm going to need to understand the trend for later. What we end up with is Planck's constant over 4 pi times 1 over the square root of I guess we'll factor out the square root of the force constant of the starting material, and then we have 1 over the square root of our reduced mass for HA divided by our reduced mass for dA. Okay, so for looking at this number, the reduced mass for the HA bond is going to be constant, and that's going to be constant as well. But what's really going to change as the reaction develops is this force constant, all right? Because when we get to the transition state, the vibration between the proton and atom A will have changed. It will have gotten different. The force constant will have changed. All right. So let's, what I want to communicate by this math is just that your difference in 0-point energies for proton versus deuterium are related to the force constant for the vibration. Okay. So, in this case, what we have said is that our transition state looks like the proton is sort of being evenly shared between A and B. And if we were to draw a new symmetrical vibration that develops in this transition state, it would involve A and B sort of vibrating away from each other, and the proton stays more or less motionless. Now, the force constant at the transition state is going to be different than the force constant of the starting material, because the force constant at the starting material was just the HA vibration, and now at the transition state it's A and B vibrating, and actually the proton isn't really even moving. Okay. And if the force constant at the transition state is different from the force constant in the starting material, that means that ZPE difference, the 0-point energy difference in the transition state, will be much different than 0-point energy difference in the starting material. In this case, because we've said that the vibration that matters in the transition state is this symmetrical stretch, and because we've said that that stretch doesn't involve movement of the proton at all, you wouldn't expect to see much of a mass-based difference. I need to move some stuff around. You wouldn't expect to see as much of a mass-based difference in 0-point energies if the proton isn't even moving. So again, we're going to take a cross-section. Again, we're going to draw a potential energy well that represents vibration, this symmetric stretch vibration, which is the one that develops newly in the transition state. And I think I wanted this to be, roughly right here. Oops. And because this vibration doesn't involve a lot of motion of the proton or the deuterium, here is where the 0 point energy for the deuterium is, and here is where the 0 point energy for the proton is. And our 0 point energy in our transition state is small. Okay? Let's see what that does for our reaction and our reaction rates. But let me pause because I realize the setup here is a lot to take in. Let's pause for questions. Yeah, Austin.
What's the, I guess just to get a framework, what's the comparison of frequency of vibration versus speed of reaction?
Speed of reaction, that's a good question. What is the comparison of the frequency of vibration versus the speed of the reaction? The speed of the reaction is just determined by this energy barrier. Now, the frequency of vibration for deuterium versus proton is going to determine the relative heights of those barriers for a bond with deuterium versus a bond with hydrogen. And that will potentially allow us to do an experiment where we say, let's replace that proton with deuterium and see how that affects the rate. And if we observe an effect, then we can say something about whether or not that proton is involved in the rate determining transition state of the rate determining step. Kim.
I guess I'm just trying to put a context around this. I felt like I was following until we started talking about deuterium again. Are we trying to show how the rate constant ratio is going to be different for this made up reaction that we made? Or
Yeah, what I'm trying to show you is when we can expect. What I'm trying to show you is when we can expect to see a large isotope effect.
Okay. And
in order for that to be the case, in order for us to observe a large isotope effect, the difference in 0 point energies in the starting material have to be different from the difference in 0 point energies in the transition state. And the way that you see a difference in those 0 point energies from starting material to transition state is, and I'm sorry because this is difference of a difference. But Kim, this is your whole research, so it shouldn't be a problem. Right. I mean, it'll make a little bit more sense when I map it out, and when we're through with the discussion. But I'm trying to show you the situations in which you can expect this 0 point energy difference to be bigger than this 0 point energy difference, such that the rates will be different. I'm going to show you why that's the case. So let's just start with the proton reaction. I'm going to go ahead and draw a dotted line to represent this energy level that we start at if we're in the proton. And then I'm going to draw another dotted line here to represent the energy level of the vibration in the transition state that matters. Okay, and then this arrow is going to represent the activation energy for the reaction with the proton. Make sense? Okay. Similarly, we can do the same thing for the deuterium. Dot, 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 dot. And this energy difference here is the activation energy for the reaction with deuterium. Now, based on what I've told you, which reaction is faster? The reaction goes faster for hydrogen or deuterium? Hydrogen. You can tell that because this energy difference is smaller than that energy difference. But it turns out that if we compare that difference in activation energy, if we do activation energy for deuterium minus the activation energy for a proton, mathematically, that's exactly the same as taking the 0-point energy difference in the starting material minus the 0 point, I don't know, I need a different color for transition state, minus the 0 point energy in the transition state. It's, you can prove it to yourself mathematically. It's just two different ways of subtracting four numbers from each other. Okay? Kind of a double mutant cycle, Kim. So, and if we want to be even more confusing, I suppose that we could call these individual ZPE energy differences delta ZPE for the starting material. If you like that better, we could call this delta ZPE for the transition state. And then we could call this some new, if you like deltas, if you like Greek letters, delta ZPE. But if this delta ZPE is greater than 0, then activation energy for deuterium is greater than activation energy for proton. Then rate constant for deuterium is slower than rate constant for proton. Then ratio of rate constant for proton over rate constant for deuterium should be greater than 1. All right, that was a lot. Let's pause, take a step back, because this is going to be important for what we talk about for the rest of the day. A take-home message is we're only going to see a large kinetic isotope effect if there's a major change in the vibration between the starting material and the transition state. For example, if a vibration gets weaker, if the force constant changes. And we're only, okay, yeah, let me try again. We're only going to see a sizable kinetic isotope effect if there is a difference in the vibrational mode that the transition state can adopt versus what the starting material can adopt. And that could be because situations where you would see a difference would be if the sense of the vibration changes completely, right? We used to have HA vibration and H was moving. Now in the transition state, H is motionless. That's a big change. Or a particular vibration could get stronger. The frequency, a particular vibrational mode could get a stronger force constant because the new structural context was stiffer, as an example, versus more flexible. All right. Yeah.
So are these like vibrational modes something that you should be able to like figure out looking at starting material and transition states?
Yeah, so you're getting to the therefore what, and I can't figure it out in the text yet.
Okay.
I mean, so what should you be able to do as an example because of this? I think this is about giving you the tools to rationalize experimental results when you do the experiments. All right. So if you did a kinetic isotope experiment and you observed KH over KD equals 1, you would conclude that there wasn't a lot of difference in the vibrational modes available to the starting material versus the transition state. Which could be because that proton just isn't involved. It doesn't change in the transition state. Maybe it's not involved in the rate determining step. Or it might be that the transition state is close in energy to the starting material, so it resembles it closely. Right? I have in my notes, okay, but I want to pause to let you ask some follow-up questions. Paul the Apostle said something about how when we don't know what to pray or ask, the Holy Spirit does so for us. So I will invite him to tell me what's on your minds. I'm guessing this is still a little confusing. So can I show you a couple of different reaction coordinates to show you how you might reason your way through this? I don't expect you to draw these. They are posted on I'll post them online, but it will be easier to do this if I can just go to something that I already have. There we go. Look at all that math you got to do yet. Okay. So, oops. Joshua, where are you going? I missed. I'm sorry about the craziness here. Okay. So let's imagine similar sort of diagram, but let's imagine that we have a very endothermic reaction. Hammond postulate tells you that the transition state structurally must resemble the starting material. Therefore, the vibrations you have in the transition state should resemble the vibrations you have in the starting material. The frequencies and the force constants should be similar because the geometry is similar. That means the difference in 0-point energies for hydrogen versus deuterium should be similar in the starting material and in the transition state. That's going to mean that these activation energies are similar, which is going to mean that the rates are similar, which is going to mean we don't observe a very, very large kinetic isotope effect. Does that make sense? Okay. Let's imagine a case where the reaction is crazy endothermic, very uphill. Here, our transition state is closer in energy to the product, so the vibrations in the transition state are going to resemble the vibrations in the product. Okay? Now, suppose this is just a proton transfer reaction. We're going from HA and B to A minus and HB. And suppose that the bonds here and there have similar force constants. If that's true, we might be again in a situation where the 0-point energy difference here is not that different than it is here. Activation energies for hydrogen and deuterium are similar, and kinetic isotope effect is small. So these are two situations. If you do a kinetic isotope effect experiment and you observe that the number is small, maybe you conclude the vibrations in the transition state are similar, either similar in nature or strength to the vibrations in the starting material. Yeah?
How can you decide that the product and the reactant have similar force constants?
We're pretending that that's the case. This is the example the book gave you, and I had that same question. The question is, how do you know that these two vibrations for starting material and product should have similar force constants? They're presuming that that's the case. So
Can we presume that there would be a case for that?
I think so. I think so. I mean, so what this would be is you do the reaction, you know it's endothermic, but you don't see a kinetic isotope effect. You know that the transition state shouldn't resemble the product, so the only way you don't get a kinetic isotope effect is if the vibrations in the products are actually similar to the vibrations in the starting material. Okay? And then the case we started with was, let's just imagine it's thermoneutral, and that's where The transition state is not early, close to starting materials. It's not late, close to product. It's somewhere in the middle, Goldilocks, just right, right? And in that case, you might observe a large change in the vibrations of the transition state versus the starting material, and then you'll observe a larger kinetic isotope effect. Yeah?
I might be spacing again, but what's the point of kinetic isotope effect in the first place? Again?
What is the whole point of the kinetic isotope effect? It's to try to get a sense for what bonds are being formed or broken in the transition state.
Okay, but it's not as straightforward as that, because if the bonds, even if a bond is broken and formed, if it has similar vibrational modes, you can't really tell.
That's right.
Okay.
Yeah, so it's in some cases, in some ways, the best you can do to try to figure out whether this proton is involved in the transition state of the rate determining step. Okay, and there's a lot more details in your book. If you need to understand this at a higher level, keep the book and you can dig back into it when the time comes. What we've talked about here, I'll go back to our notes. What we've talked about so far, this has all been, has all, can you just, has all been, new contraction, folks, for reactions where the bond, where a bond involving a proton and whatever group is changing in the rate determining step. And in those cases, we might observe a large kinetic isotope effect, and when it comes from a proton involved bond that's changing in the transition state, we call that a primary kinetic isotope effect. I will never write out primary. I will do one with a little degree sign. I cannot remember when I learned that that meant primary, but it's easier. So there you go. There's a class of smaller kinetic isotope effects that are called secondary kinetic isotope effects. And these come from isotopic substitution at an atom that is not at an atom in a bond that is not being broken in the transition state of the rate determining step. A lot of prepositions there. Secondary kinetic isotope effects occur when a proton's not being pulled off or a new bond being formed at that proton in the transition state, but that proton is attached to something else that is changing in the transition state of the rate determining step. And the classic example of this is something called rehybridization. As an example, we know for that in the E2 reaction, this carbon is going to be going from sp3 to sp2 in the product. Okay. Now, if we did isotopic substitution here, we might, if we did isotopic substitution there, we might expect to see a primary kinetic isotope effect. If we did isotopic substitution at the alpha carbon relative to the heteroatom, we would expect to see maybe a secondary kinetic isotope effect. So let me show you how this might happen.
Can you say one more time the secondary kinetic isotope effect? We're replacing one of the hydrogens with the other hydrogen?
I'm sorry. I just mean if we were to replace hydrogen versus deuterium at the carbon where the hydrogen's being removed during the reaction versus doing the same thing at a hydrogen that's not directly involved in the reaction. All right. So to understand the origin of these kinetic isotope effects, we're again going to consider vibration. And remember that the data we're getting here are just from the same reaction repeated with deuterium in one spot versus deuterium not in that spot. So if we did the experiment here on this alpha carbon, we're going to get a different kinetic isotope effect than if we do the experiment on this beta carbon, even if it's the same reaction. All right, so let's think about what's changing in terms of vibrational modes for a proton that is attached to an sp3 hybridized carbon. Going to be real general here. Here's an sp3 hybridized carbon. Sorry. And we're going to consider a couple of different bends that tend to happen for sp3 hybridized carbon hydrogen bonds. In-plane bend and out-of-plane bend. Again, this is stuff from PChem that no idea. I usually don't even ever think about atoms vibrating, but they do. So the in-plane bend for this proton would be it wagging this way and then that way. Okay, in the plane of the board. That's why it's called the in-plane bend. However, there is a equal in energy bend that can occur out of the plane, and this is hard to draw. This is where the hydrogen comes out at you, so we're going to draw a wedge kind of arrow, and then the hydrogen goes back into the page, so we're going to draw a dash kind of arrow. Front, then back. Near, then far. Okay? So for an sp3 hybridized carbon, those bond vibrations are very similar. In fact, you can tell that just by looking at where they absorb in the IR, and that's 1350 wave number. All right. Wave number is directly proportional to frequency, which is directly proportional to energy. Now let's consider this analogous vibration at an sp2 hybridized carbon, a proton involved in a double bond. And for this drawing, these other endpoints just represent places for substitution. They don't represent specific carbons or methyl groups or whatever. So in the sp2 hybridized carbon, the in-plane bend would be, again, in the plane of the board, proton wags this way and then that way, just sort of waving at you. I don't know why they call it a wave. And it turns out that the sterics of that situation are not that different than the sterics of an sp3 hybridized carbon. Protons still bumping into stuff, and so the vibrational frequency is about the same. In contrast, for the sp2 hybridized carbon-hydrogen bond, the out-of-plane vibration is much freer. And we'll represent that again with the large arrow sort of going this way and the large arrow going that way. Just think of it like this. In the sp3 hybridized carbon, the out-of-plane bend started to bump into methyl groups because that carbon is tetrahedral. However, in the sp2 hybridized carbon-hydrogen bond, the out-of-plane bend is much freer because the thing on the other side of it is trigonal planar, so there's a lot more space before it starts to experience repulsion. So this is a freer, looser vibration. Freer is probably not a word. More free, and its frequency, because it is freer, looser, its force constant is lower, and that means its vibrational frequency is lower. This vibrates at 800 wave number, which is substantially that way. Go ahead.
So, being more free pretty much allows these hydrogens to swing further before they come back, and therefore they don't swing as many times per second.
I guess so. That's a nice way of thinking about it, yeah. Okay. So as you go from, if you think about a reaction in which you go from an sp3 hybridized carbon hydrogen bond to an sp2 hybridized carbon hydrogen bond, what you're going to observe, and I'm going to abbreviate our drawing because I want to. I'm going to just superimpose that vibrational potential energy well right on the place where the starting material is. You just have to pretend that that is perpendicular to the reaction coordinate. Here is our stiffer vibration where the frequency is around 1350 wave number. The larger the force constant, the larger the difference we're going to expect between carbon deuterium versus carbon hydrogen, right? And this is our difference in 0-point energies for the sp3 hybridized carbon. And then let's imagine in the transition state, or rather let's imagine in the products what it looks like, what the vibrational well looks like when we've got the sp2 hybridized carbon. We've said that the vibration is more free, lower, looser force constant, and therefore lower frequency. And that should mean that the 0-point energy difference between carbon and deuterium versus carbon and hydrogen at the end of the reaction, this delta ZPE for the sp2 product is small. If we've got a large development of, if the transition state has lots of sp2 character where we've attached our deuterium, then, and so here's the vibrational energy well representing the transition state. Here's carbon deuterium, here's carbon hydrogen. They're not as similar as they are in the products, but the delta ZPE for the transition state is smaller than the delta ZPE for the starting materials. Okay, so in that case, we might observe a kinetic isotope effect. And secondary kinetic isotope effect. All right, so this is for going from sp3 to sp2. You're going from a stronger force constant to a weaker force constant. Now, the effect of this kinetic isotope is smaller than that of a primary kinetic isotope effect. So you tend to observe anywhere from 1 to 1.4. So you're talking about pretty small numbers. And fortunately, the techniques that we use to do these kinds of experiments, in particular NMR, are highly sensitive to protons, and so we can measure small differences. Yeah?
Wouldn't that, in order for the transition state to have a lot of sp2 character, wouldn't it need to be closer in energy to the products?
Yeah, I've shown it as sort of midway through. But you can think of things on a continuum. As you moved it closer to the starting material, you'd expect to see less of an effect. If you moved it closer to the product, you maybe would expect to see more of an effect. This is called a normal secondary kinetic isotope effect, I believe. Am I getting that right? Yes. Because the rate is faster for proton than it is for deuterium, but it's still smaller than primary kinetic isotope effect. Now, if you did a reaction, let's consider, oh, we're out of time. So consider while you think over the next couple days, what kind of an effect should you observe if you go from an sp2 hybridized carbon to an sp3? All right. Fun, fun, fun. It's going to get worse before it gets better.